is a very exciting work on the local Lindbladian decoders for surface code.
Yeah.
And generally topological code segments. Yeah.
Thank you. Thanks, organizers, for inviting me. This has been super fun. Yeah, I'm going to be talking about some stuff which is a bit thematically distinct from the other talks today. Hopefully that'll be okay. It's going to be very non-technical, so hopefully people who don't work on this stuff will still be able to follow. But let me know if that's not the case. So yeah, this talk is going to be about some questions that I've been thinking about on and off for the last year or so in the study of non-equilibrium phases of matter. Okay, so these are systems which do interesting things, have some collective order that is either because of or in spite of coupling to an external environment and interaction in an open system way. Okay. As kind of a preview, the sorts of questions that we're going to be thinking about are how can information be encoded in physical, locally interacting systems? How can systems like this protect information against noise? What are the different ways in which these things can happen? And are these kind of systems which do these things useful for anything? So these are the questions we'll be thinking about. To kind of get warmed up, I decided I would do a little brief intro and tell you about some of these things in classical systems. The talk is going to be about quantum systems, but I kind of find some of these subjects entertaining, and I thought I would start off the talk by talking about classical stuff. Okay, so when we're thinking about non-equilibrium systems and emergent phenomena in classical systems, usually a really good framework for thinking about these kinds of questions is that of cellular automata. So maybe most people know what these are, but the very succinct definition is on the screen. So we have a spin model that's defined on a lattice, usually in discrete time. And at each time step, a given spin is updated in a way which depends on the spins of values of the spins on its nearest neighbors. Okay, so it's some local dynamics defined according to some update rule. And cellular automaton are capable of really complicated, fascinating, emergent behavior. So maybe some of these examples you guys have seen before. I wanted to show a particular example that is maybe the most famous example, but will kind of set the stage for the kinds of questions we'll be thinking about, which is the game of life. So maybe the exact rule here is not so important. I'm just going to show you a video, and that will suffice for now. So we have a grid of cells. The white ones are zeros, say, and the black ones are ones. They evolve according to some update rule. And when you initialize them on this very specific initial configuration, this is what happens. So I'm just evolving this in time. What's happening is that this structure down here on the bottom left is producing these little wiggling organisms that shoot up diagonally, and they just keep moving. So we're on a torus, so they're coming back, right? And if left undisturbed, this gadget just produces these little organisms forever, okay? And you can construct these increasingly baroque configurations which have many of these organisms all moving around, and you can do universal computation, and if you arrange them in sufficiently complicated ways, and there's this whole rich landscape of possibilities that that emerge in this system. So as someone who does condensed matter physics, I look at this and this is extremely cool to me. You have very complex, interesting behavior emerging from simple rules. But okay, since I'm a condensed matter physicist, I would immediately ask these two questions. So if I am looking at this phenomenon, if I want to answer whether or not it's physically meaningful, I need to address two questions. One is this phenomenon robust against noise in the system? And the other thing is this phenomenon robust with respect to having the updates be asynchronous? Okay, so I said the rules in which the cellular automaton were defined were in discrete time. At every time step, all of the cells update at the exact same time. And that's not physical. That's not a local way of doing dynamics. And so as a condensed matter physicist, I want to understand whether or not that feature is essential. Okay, so I mean, the talk is not going to be about the game of life, but let's just see what happens in this case. Okay, so what I'm going to do here is I'm going to do the same animation, but now I'm going to add a very, very small probability of having each spin flip to a random value. And the strength of the probability for that to happen at a given site is going to be 10 to the minus 5. So a very small amount of noise. Okay, so let's see what happens. So it produces one glider, and then it just totally got killed, right? So you probably can't even see where the noise is happening because it's so rare. But there was one noise event here that struck this little computation thing as it was being built, and it just completely killed everything. Okay, so the game of life is an extremely fine-tuned, fragile, non-robust phenomenon. Okay, that's with respect to noise. You can imagine we're not going to have any luck if we do things asynchronously either. So here, what I'm going to do is I'm going to update them in the way that I would be updating cells in according to Glauber dynamics or something. I'd randomly pick a site, update that site, and then randomly choose a different site. And here's what happens. Yeah, so we didn't even produce one of these little organisms. It's kind of interesting. Like you can ask what the statistics of this slime blob are, but it's definitely the structure is gone, right? Okay. So it turns out that coming up with a local asynchronous cellular automaton which can do anything and can resist noise is extremely hard. It's hard because if you want to have any structure which is preserved, you need to be capable of doing error correction in a collective way. Okay, so every cell in this lattice needs to participate in some larger computation, but the computation that it's participating in is much larger than it itself, and so one individual cell can't really understand the computation that it's being part of. Okay, so the challenge is to try to construct these rules where error correction can still be done in a sort of emergent collective way. Okay. So that's not going to work in the game of life, but we can try to think of other ways of in which it might be. Okay, so here's a summary of what's known. This is basically a summary of all the known ways of doing this. So there's one cellular automaton due to a Soviet mathematician, Andrei Tum, that was invented in 1980. What it does is it remembers a single bit of information in 2 or more dimensions. Then there are some other ways of doing that I came across last year, what I'm not going to talk about in this talk. And then there's an infamous sort of example constructed by another mathematician in 1 dimension, but it's not understood by anyone except the author of the paper, which is unfortunate. So we don't really have any examples, actually. So I think this is a very fundamental question. I think physicists will have a lot to say about these questions. Coming up with this example wasn't that hard. I think when we approach this question from the point of view of a physicist, I think we can make a lot of progress. But for now, there's not much that's known. Yeah.
One or the other.
So the 3 examples here are all designed for noise, and the first and the third one are also resist asynchronicity, and the second one there are some examples of models that naturally resist asynchronicity and some which don't. It's not well understood at all. We just have a few isolated examples. So coming up with a general theory is something I think is super interesting, but is not. We don't understand the situation well enough to make any good statements. Yeah. Okay. Okay, that's the end of our intro and to get people warmed up. And the talk is going to be about quantum collective memory, right? So the problem is going to be almost strictly harder, and we didn't have that many examples in the classical case, but we're going to talk about the quantum case nevertheless. So the question we're asking is, we're just going to be focused on memory, and we're going to be asking what kind of locally interacting systems can collectively and robustly remember a single qubit of information. Okay. Now, the setting in which we're going to address this question is going to be in the context of the surface code. So hopefully everyone so familiar with this. So this is a surface code. We have a 2D surface. We have anions on the surface, right? And when we do error correction, we want what error correction consists of taking these anions, the via way which eliminates them. So what we'd want to do as part of preserving this memory is we'd want to, take these anions and pair them up in a way like this, right? And then hopefully people know that if I pair the anions up in a way like this, which connects different sides of the surface, then there's a logical error is produced. Okay, so sorry, I didn't plan any review of the surface code. I hope that's okay. Okay, so we want to come up with a local collective process which performs this kind of error correction. So before telling you some proposals of how to do that, I wanted to kind of review how error correction is actually done in the real world, right? At least as of now. So how error correction is done is as follows. We have a quantum computer here. Our surface code is sitting in the quantum computer. Measurements are performed on the surface code. The results of those measurements are fed into this classical computer sitting outside of the quantum computer. It crunches a bunch of numbers, does some decoding algorithm, and then performs feedback on the quantum computer. Okay, so this is kind of the workflow. Just to illustrate this with a picture, here's a picture of Google's device. You have the Dill fridge hanging down here. The quantum computer is in the center of that thing. And then all this crap, all the blue cables are used to transmit the information out of the quantum computer to the classical stack sitting in the back, and then control, and then things are fed back into the quantum computer later. Okay, so how is error correction actually done? Like, what does the classical computer do with these syndrome information? Well, what's done right now is there's information about the total space-time history of all the anions in the surface code. And then it does this algorithm called minimal weight perfect matching on the history of the syndromes that it accumulates. So you accumulated a bunch of data for the whole history of your experiment, however long you're keeping the memory there for. And then at the end, you apply this matching algorithm to the whole history. Okay, so that's how things are done. So the current way of doing error correction is obviously not going to fit within the kind of framework that we're looking for, right? We're looking for a system which locally performs error correction, which autonomously performs error correction. And this algorithm is just described as very non-local, right? Everything is going into this classical computer. You're doing a very complicated non-local computation and then bringing stuff back. Okay, so this is not thinking about these kinds of algorithms as done currently is not going to teach us anything about non-equilibrium phases of matter or anything like that. Okay, but I also wanted to. I mean, this is not really a experimentally motivated conference, but I also wanted to mention that there are significant practical drawbacks to doing error correction in the way that it's currently done. Okay, so one drawback is this whole process is very non-local, and you suffer a lot of latency when you're transferring all this information from place. And actually, the more pernicious problem is that you have to have a lot of these control lines which transmit information about your measurements outside of the quantum computer to the classical one. And those heat up the quantum computer quite a lot, actually. Just the act of passing information through these wires heats everything up. So all these wires are very bad, right? So they just generate a ton of heat, and your Dill fridge doesn't have a lot of cooling power, and this is bad. So in order to the people that do experiment that I talk to tell me that we're going to have to put the error correction stuff inside the fridge to eliminate all these wires, or at least most of them. So when we get to surface codes of maybe 1,000-ish qubits or more, the wiring is just not going to be scalable. Everything's going to have to go inside the fridge. Okay. Given that, however, we realize that the current ways of doing error correction are just not going to work, because Dill fridges basically can't cool stuff very quickly at all. there's no way in which you're going to it's impossible to take a CPU and stick it inside of the dill fridge and not completely overheat all of your qubits. Okay, so CPUs are never going inside. So we're not this error correction process I described, where you store this big history and then you do minimal weight matching on the history. That's not going to work. Okay, so what we need is an error correction algorithm which can go inside the fridge. It has to be fast and accurate, like any good error correction algorithm. It also has to be extremely simple. So we need to run it on hardware that is way, way, way simpler than a CPU, right? It needs to be some extremely simple thing. So, okay. Another way of describing what we want is we want something that looks like this, okay? So imagine we have a setup where we have our qubits and our surface code. And then next to each qubit, or maybe next to each location of each stabilizer, we put a really small classical processor. Okay, so those are these purple boxes, right? These processors can maybe measure stabilizers that they're close to and perform feedback on the qubits that they're close to. And they can communicate with their neighbors, but that's all, okay? And ideally, they run a very simple computer program, which can be described with only a small number of bits, right? If we have this kind of a setup, we can stick this inside the dill fridge. Each of these guys is not going to dissipate any heat if it's running a very simple program. And if we have a way of doing error correction like this, then we'll be able to have a error correction algorithm which is actually scalable and which can go inside of these big size surface codes. Okay. Ways of doing error correction like this are called cellular automaton decoders in the literature. And the similarity to the cellular automaton I was talking about should be clear, right? You're making local feedback based on local update rules. Okay. Okay, so what's known about cellular automaton? Yeah.
Again, just keeping with the sort of practical
Yeah.
solution. Is it doing that this like having lots of these small units actually produces less heat than having like one large computer?
Yeah, so you have maybe 2,000 bits per processor an allowance. If you're operating at superconducting timescales where you're doing error correction on hundreds of megahertz timescales, the allowance you have is maybe about 1,000 or so bits per processor, something like that. Modulo the development of like cryo CMOS technology that anyway, it turns out a lot of experimentalists are actually working on building ultra cold logic devices that you can stick inside the fridges, and they're built out of like superconducting circuits or something themselves. And so there's a bunch of hardware stuff, but if you just take the stuff you can buy today from ASIC or whatever, and you try and stick things in there, you get a couple, maybe 1,000 bits.
I guess I meant more like the scaling of like one big thing with one small thing, because it gives you like quite a different scaling. Like,
yeah, okay, so we're not going to be able to make, if any of these dissipates any non-zero amount of power, we cannot make an infinite surface. Cooling power of a dill fridge is fixed, right? People tell me we're never really going to build a surface code with a system size of more than like 50 or so. So that's kind of like the upper size that you have to consider. Past that, we're just going to have multiple surface codes, and they're going to be interlinked with stuff. 50 by 50, yeah. So that's already thousands of cubes. So that's
more than
you want your 10 to the minus 12 logical error rate, and that's enough to do that. And my thousands of bits figure was arrived at saying, okay, let's take a 50 by 50 surface code and not have it overheat in the dill fridge. I can't believe I'm talking about this at this conference, but anyway, maybe we can just, as theoretically inclined people, we can accept that this is good enough motivation to think about these. Yeah. Okay. I wanted to do a brief survey of what's known about existing cellular automaton decoders, just to kind of set the stage a bit. There are kind of two strategies have adopted to doing error correction in a distributed way. One approach, which I'm not really going to do justice to, is sort of a hierarchical approach. So this was the first cellular automaton decoder kind of followed this. It was introduced by Harrington back in 2001 or something in his thesis. And it operates according to some kind of block spin-ish RG type way of operating. So you have anyons, and it tries to group anyons into like coarse-grained clusters, and then take those clusters of anyons and group them into further coarse-grained clusters and try to do sort of RG on the distribution of anyons, according to this sort of mysterious picture. Last year with Shankar and Margarita, we came up with what I'll just, for the purposes of this talk, call it an improved version of Harrington's decoder, which also worked according to this kind of general philosophy. There are a few problems with this way of doing things, though. One problem for me as a condensed matter person is that the way of doing error correction in these approaches is not space or time. And really what I'm interested in at the end of the day is thinking about non-equilibrium quantum phases of matter. And I don't really want to consider something which has no translation symmetry in any sense to be a phase of matter. One other problem is that these decoders are naturally only defined on system sizes, which are like a power of an integer. So 3, 9, 27, etc. That is a huge pain because it means like when you do numerics, you're only limited to a very special number of system sizes. And certainly when Google builds their device, they don't want to be restricted to 3 by 3 or 9 by 9 systems. So that's a problem. They also have really bad thresholds. So the threshold for Harrington, there hasn't been a proof of a threshold in Harrington's decoder, but if there is one, it's not that great. The threshold in our model is even worse. It's no bigger than 10 to the minus 4, which is not great. So practically there's some issues as well. Yeah, I think translation invariance in space is maybe not super a big deal, but translation invariance in time I feel is more important. If we're talking about a phase of matter, we're thinking about there's a generator of the dynamics, and if that generator of dynamics is allowed to vary according to some arbitrarily complicated function in time, then what are we really studying, right? We have then we're opening the floodgates to you consider an arbitrarily time-dependent operator, and then yeah, I don't know how that fits within the framework of normal physics.
Your figure on the right. So what is S?
Don't pay. Please, let's not talk about the figure on the right.
It's your figure.
I would. So the figure on the right is an illustration of a really horrible memory in practice. So it has very poor scaling of the logical error rate with physical error rate. Let's not. If you really want to talk about it, let's talk about it offline. But I'm just throwing shade on my own work, so I think that's okay. What I do want to talk about is a different category of approaches. Really, it's just been one pair of papers, which is much closer to what I talked about today, and which, as a physicist, I like a lot more. And the idea is very simple. So remember, we have this. We have our qubits, and then we have an array of processors, which do local measurements and feedback. And what we do is we use the idea is to use the processors to simulate some attractive interaction between anyons, which makes them pair up and eliminate themselves. Okay, so we just need to have anyons be attracted to one another, and then anyons won't be able to get too far apart and cause a logical error. Okay, so we would want the processors to set up some kind of like potential field like this and have anyons be attracted to one another. The best proposal in this direction so far was by basically a bunch and some other people back about 10 years ago, and what they did is they used dynamics that was where this attractive interaction between anyons was mediated by a scalar field that was updated according to some Poisson equation. So you have like a Poisson equation that has anyons as a source term, and that introduces some attractive interaction between the anyons. I think this is the most natural thing to try as a physicist. However, unfortunately, there are problems with their proposal. So for reasons I'm not going to get into, it required a communication speed between processors which diverged with the system size, which may be practically okay, but again, as the perspective of a condensed matter physicist, I don't want to have non-local diverging interactions speeds. One other problem is that the arrays of processors had to live in 3 dimensions. That's not a huge deal. And then they also, unfortunately, only give numerical evidence for error correction in their paper. And as we'll see, interpreting some of these numerics can be quite delicate. Okay, but we're going to take that idea as a starting point for the rest of the talk. Okay, hope that makes sense. As kind of just a summary table, maybe this is too much information, but here's the kind of landscape of stuff that exists so far. These are the kind of desired properties we might want to have. Serial SYN is this thing that I worked on last year. And what we're going to do today is we're not going to check all the boxes, but we're going to check the ones that I care about most. And then checking the remainder is going to be left for future work.
What is this like the post X? And
Oh yeah, I should have explained. So X means X in 2 dimensions and check in 3 dimensions. Sorry, I probably shouldn't have drawn this, but
What do you mean by classically robust?
yes, classically robust. So I mean, it's robust with respect to errors on the classical processors. So
like, let's say if your time ticker clock
yeah.
is wrong.
Yeah, or the processors are going to like take in syndrome data and then transmit that data somewhere else. Maybe that data gets corrupted during the course of transmission. Let me explain the 2 things we're not going to do. So the first concession is we're making this assumption. We're assuming that there's no noise in the classical system, right? Experimentally, that's fine. And theoretically, it's very hard to relax. So theoretically, it's unsavory and very difficult to deal with. And for those reasons, I'm not going to worry about doing it in this talk. Okay. If you want to kind of like get a framework for these kind of systems, you might call them like classically controlled phases of matter. So we have this classical control architecture, which is still local, and it's manipulating a quantum system and getting the quantum system to do something robust. But the existence of this quantum phase depends on there being this classical reliable thing there. Okay, that's our first concession. Second concession is that we're going to allow the number of bits stored by each processor to diverge slowly with system size. Okay, so this is also theoretically unsavory and annoying to deal with, but experimentally okay. So yeah, if people are really bothered by this, we can talk later about some ideas of how to fix this, but for now, we're going to let the sizes of the processors grow with system size. Okay, so sorry to some people in the audience that clearly don't like it, but we're going to do this anyway. Okay, so now I'm going to tell you about how the construction actually works and how we get a memory. Okay. Any other questions on like the setup, general stuff? Okay. Okay, I'm going to talk about, yeah, sorry. So the first problem I'm going to talk about is a slightly easier problem when it comes to thinking about quantum memories. And that's the offline decoding problem. Okay, so when we think about quantum memories, there are 2 types of decoding problems, and this is the simpler one. So we're going to imagine we're doing communication over a noisy channel. Okay, so A has a quantum state, a logical state of the surface code in this case, and it's trying to communicate it to B. And it's communicated over a noisy channel, so the state experiences some error given by this channel, error channel E. And B wants to undo the noise and decode the noise and get the logical state that A sent. Okay, so the goal is to undo the error channel. Okay. So what we're trying to do is we're trying to minimize the error rate defined in this way. So we're trying to come up with a channel D such that it approximately undoes the effects of noise for any noise that happens to be applied. Okay. And our assumptions are that we are kind of perfect in our attempts to undo the noise. So we have perfect measurements and we don't introduce any noise into the state when we try to do the error correction. Okay. So we're going to call this the offline decoding problem. I get this noisy state and I just try to get rid of the noise. Yeah. What is online decoding? Yeah. Yeah, we're gonna do offline decoding as a warm-up. And then once you understand this, the understanding online decoding will be easy. Of course, what we're really interested in the end of the day is we have a noisy quantum computer. Noise is always happening. Measurements are faulty, and we're trying to maintain a memory in it. That's different from this task that I just discussed. This one's easier, but we're gonna solve the easier one first, and then we'll solve the harder one. Yeah. Okay, good. The very brief discussion of physical significance. So if people are interested in like open phases of matter and stuff, I don't want to get into a detailed discussion of this, but if you can find a local Lindbladian that undoes errors like this, you have a way of kind of building up mixed states which are in the same phase as one another. This is just for the people who already have been thinking about this. Okay, here's a simple strategy that we might apply for doing decoding. Okay, it's going to be non-local, but I'll discuss how to make it local in a second. So the non-local strategy is take every anion and have it move in the direction of the anion closest to it until it annihilates with something. Okay, so this is supposed to be a proxy for getting a minimal weight perfect matching. All right. So in this picture, suppose we have these three anion pairs in the system. The anions would just move in the direction of the arrows shown. Okay. So this does not like immediately create a perfect matching. What's going to happen? These guys will annihilate. These guys will annihilate. And this guy will like initially start to move to this one because it's closer here. But then after those annihilate, it'll like come back and kill this one, right? So this is supposed to be some distributed way of computing a proxy to a minimal weight matching. Okay. And one can show that this actually indeed has a threshold. So if you do this thing of just moving towards the closest anion, you correct errors with a high probability, as long as the noise is weak enough. Okay. Good. Now there's a very simple way of doing this locally, and it uses these classical processors, and here's how it works. So we have an anion here sitting in a grid. Each side of the grid is going to have this like classical processor, right? Okay. And here are the rules. So an anion is going to send out messages that broadcast its location. The messages you're going to have one message on each of these processors, and the message is going to take an integer value. When messages move, they increase their value by 1. Therefore, the value of a message will indicate how long the message has been propagating for. Okay. And then what you do is anions emit and receive these messages, and they just move in the direction of the smallest message that they receive. Okay. So for example, if I as an anion receive a message coming from the right, I know that there was some anion over on the right, and I move in that direction. Right. So in time, it might look like this. This anion first sends out some messages. They indicate that this message was a distance 1 from the anion which sent it out. At the next time step, they propagate like this, and so on and so forth. Yeah.
Receiving just means that the animal looks around its neighbors and whatever that the smallest message.
Yeah. Really, you just look at your own site. So the anion just looks at the site it's at and says, out of all the messages that reach this site, which one has been propagated for the least time? That gives it an idea of where the closest anion to it is, right? Does that make sense? I'm not sure.
Like looking around like these sides around it and like whatever the smallest message coming there.
Yeah, as long as you ignore messages that you yourself sent out, right? So
I know the point is that those will all be the same, so then they stay there.
yeah, you could think about it like that. Yeah. It doesn't matter exactly how you do it. Just the general idea is you send out messages and you move in the direction of messages you get. So the exact framework is maybe not super complicated, super important. Okay. So let's just watch a movie of this happening, because then maybe it'll be more intuitive. So I'm going to start with a completely random state with a large number of anions just to make the animation look nice. And I'm just going to do this message passing dynamic. The color is going to indicate the inverse strength of the message, okay, or the inverse value of the message. You'll see, it'll be obvious once I run it. Okay, so this is what happens. So this is asynchronous update. we're choosing sites at random to have these guys move around, and eventually they just meet up with anyons and are annihilated, right? So it's not surprising that this works, I guess. We're just trying to do we're essentially doing a time delayed message mediated version of move towards your closest anion. Okay, cool. Ooh, oh, sorry, I pressed escape key.
Message.
Yeah.
Like, does the message ever get like die out, or will it just move?
Yeah. So the way in which messages die out is that they're like a message that has been moving for longer gets overwritten by a message which has been moving for less time.
Ah, I see.
So like basically, if you have a anion here and anion here and then one over here, the messages from the further one will get overwritten by the ones from the closer one. Yeah. And you can have them die out after a large distance if you like. Yeah. Okay, cool. So that's now one can prove the following result about this decoding scheme. This kind of is a result that you would want to prove about any error correction scheme that you come up with, right? So the theorem is that as long as your error rate is smaller than some constant value PC, then the logical failure rate is exponentially suppressed in some power of your system size. Okay, so P log is the probability of your decoder making a mistake. And furthermore, the expected time that it takes you to do all of your error corrections is a power of log of system size. Okay. So this is kind of the best you could do.
So here T is there's a one-shot error rate.
Yeah.
And then now each processor, you mean each site, there's a classical memory recording the message.
Yeah.
And that has to be roughly log-L. Can store up to log-L bits.
Oh yeah. So sorry, this is this parenthetical here. So the distance that messages can be transmitted over is the exponential of the number of bits on each site, right? Because to store a number of size L in binary, I need log L, right? So with log L bits, you can communicate across the entire system. Then you get the scaling of the error rate. If you reduce the number of bits, then you can communicate over shorter ranges, right? You'll still have a threshold as long as the range you can communicate over with is at least like log L. So you can get away with log of L bits if you want a threshold, but you can't get away with any fewer than that. Of course,
that log of L is coming from some similar flavor as like if distance is like
log L.
log L.
Yeah. I can go through that argument in more detail later if you like, but yeah, maybe we're not going to care. I mean, this diverges with L, but maybe we're not going to care about. Yeah. Okay. Cool. So that's the result. I wanted to give you a very brief flavor of like how this is proved because the proof is very simple and it's also the style of proof is very common in this kind of field of research. So I want to just give you a flavor. So the proof consists of two parts. The first part is to show that if you have an isolated group of anyons, then they are quickly annihilated. They annihilate each other very quickly, regardless of the messages that they're receiving and regardless of their environment. As long as they're isolated, they get corrected. And then the second part of the proof is to say that big clusters of anyons are very rare. Okay, so we'll see then why these two parts imply this theorem in a sec. Okay, so let me explain the first part. This is the most annoying thing to prove. But the first part is the following result. So consider a situation where I have a box in my space-time in space where I have some anyons, and suppose that box is isolated from all of the other anyons. So there are no anyons within this like annular region. Okay, so these anyons are well separated from all other anyons. Then what you prove is that the anyons in here will for sure annihilate against each other and not cause a logical error. They'll just kill each other before they meet up with any of the anyons outside of the box. And they will do so in a time which is like linear in the size of the box. Okay. So they kill each other pretty quickly, and they don't get messed up with any of the anyons outside the box, as long as these constants are chosen appropriately. Okay. So this is in the math literature, this would be called a linear erosion property. These clusters of errors are corrected in a time linear in their size. And the proof of this is like really detailed. You have to look at how the messages interact with other anyons and analysis of like what signals can be received where. It's kind of annoying, but it's not sophisticated. It's kind of a simple-minded proof. Okay, that's one thing. And then the other thing is an argument which is originally due to this Gatch guy, which is very general. Oh yeah, sorry. Yeah. So there exist these constants lambda and also this constant alpha such that this happens. So lambda will need to be sufficiently big. So easier, right? So if lambda is very big, then these guys are very, very well separated from everything else. And then they're corrected like kind of more quickly, right? If lambda is very small, then this guy can like start receiving a message from this guy, and then maybe this guy actually moves over here or something, right? They can start interacting, right? Yeah. If lambda is too big, it can't be shown. So this property is easier to show when lambda is bigger, right? Yeah, okay. Maybe we can talk about it. Or yeah, Tommy, maybe. What values of R? This holds for any R. You'll see in maybe like 2 slides which exact R's we'll apply it to. We'll apply it to the R's at many different scales to get a proof. Yeah. Yeah, good. But I mean, maybe like the intuition for this is that you know, the way in which this could fail to be true is if this guy received a signal from something outside of the box and started like moving toward the thing outside of the box, right? But this guy always moves in the direction of like the closest signal it's received. So he'll always have to receive a signal from something else in here. And so he'll always be attracted to some other anion inside the box. Yeah. Okay, yeah, maybe so then that's the first part of the proof. The second part is very general, and it's a very general probabilistic argument originally due to Gatch, which can be used in a lot of different settings. So and it's just about the structure of noise that happens in a system. Okay, so I'm going to try to define that here. So we're going to fix a number n, and we're going to define a K cluster of anyons to be a set of anyons where this is true. So they're contained in a box of size n to the k, and they're isolated from other stuff by a annulus of size n to the k plus 1. Okay, and then we have these clusters for different values of k. So these clusters get exponentially bigger as k increases, and they're exponentially more isolated from their environment as k increases. Okay, so hopefully the definition is clear. Because we're going to use that in the next slide. We're going to then renormalize the noise in the following way. So the noise is this set of places in my state where noise has acted, right? We're going to define E0 as all the qubits at which suffered noise. We're going to define E1 to take E0 and get rid of all of the 0 clusters. So 0 clusters are like these guys. They are small boxes of anyons that are isolated from other anyons. Right? Then we're going to likewise keep going up this sort of hierarchy of different cluster sizes. So we're going to define E2 as taking E1 and then getting rid of all the 1 clusters. So the 1 cluster would be like this. This would be a 1 cluster. Okay. So and the theorem that, again, this kind of general argument is originally due to Gatch, although we needed to kind of prove a refined version, is that the probability to have any noise after you've done this K levels of like sparsification here decreases extremely quickly in K. So what we're doing is some kind of like RG thing. We first get rid of the very small clusters, then we get rid of bigger clusters and so on. And the noise is killed very, very, very quickly as we do this process. Okay, yeah.
Zero clusters are two things that are close by.
Close by and like a little bit isolated from their environment.
So one cluster.
And then the one cluster is, well, the cluster, let me go back to the definition. So it's this guy. So K cluster, it fits in a box of size n to the K, and it's separated from other anyons on a scale of n to the K plus 1. Yeah. So basically, like we get rid of the zero clusters first. Then what remains are all these like big noise, which is well isolated, and then we get rid of the smallest clusters there, and then we keep going. That makes sense. So hopefully the definitions make sense. And here's the idea of the proof. So suppose we're given a bunch of anyons like this, a noisy state. The linear erosion result we proved basically says that zero clusters correct themselves. So these zero clusters are anyons which are well isolated from their surroundings and they're small, and they just correct themselves before they can influence anything else. So these zero clusters would just like will disappear under the error correcting dynamics, right? Then once the zero clusters have disappeared, we're just left with the one clusters and higher. But then the error correcting dynamics, because of this linear erosion thing, quickly kills the one clusters also. And it proceeds higher up for all levels of the noise, okay? The only way you can have a logical error in this system is if you have a cluster which has a size which is like proportional to the whole system size. This cluster is not guaranteed to be killed by the dynamics. Okay, but we have this result, the sparsity result, that says clusters of big sizes are very, very rare. So the probability for you to actually get something like this is very small. Okay, so this is kind of the structure of the argument. Okay, and this allows you to prove this threshold result. Yeah.
There's just going to be one
Yeah, I guess these guys are going to meet up with each other and kill each other. Yeah, those guys will communicate. If this is a torus, say, they'll communicate across this boundary and then they'll cause an error, right? But the only way in which an error can occur is if you have this cluster which is extremely large. And that's very unlikely. Okay. Yeah. Oh, why did I define n to be an integer? I don't know. We're on a lattice, and so I like it when my clusters have like include a definite number of sites, but it could be a real number. Yeah. Okay. Or maybe more questions on the proof. Yeah.
Does it follow from the definition that every ion is part of exactly one cluster?
So the smaller clusters are part of bigger clusters, right? So this guy is in a zero cluster, and this zero cluster is itself contained inside of a one cluster. And then this one cluster may be contained inside of an even bigger thing, right? But the point of the argument is that all the anyons in zero clusters kill themselves before they interact with any other anyons that are not in these zero clusters. So they just take themselves out of the equation. Then the same thing happens for the one clusters and stuff. So after we've done the first layer of this renormalization, then you don't have this feature. Yeah. Yeah, please.
You present your decoding in a way that you move anyons that move to each other.
Yeah.
Then if you don't move anyone, but just consider the smallest distance.
Yeah.
There,
yeah.
Essentially, is not there. That error proof still works in this thing, or there's a crucial difference.
That would work. That's not a thing you can do locally, but yeah, you could prove a threshold result using that. Yeah. You could also do, like, for example, you might wonder like, why does minimal weight perfect matching have a threshold? like you could give a proof that minimal weight perfect matching has a threshold using this same argument if you wanted to. Yeah. Cool. Okay. Okay, that was the proof. Oh, yes, one question. Yeah.
Let's say they're decoding weight, but it's impossible to figure out what the threshold is.
Well, let's just do numerics for that question. So I can give you a really horrible estimate, but I'd rather just do Monte Carlo. Yeah. So here's the requisite Monte Carlo. So when you do this in Monte Carlo, you find that these are the threshold values. So if you're doing this for the one-dimensional repetition code, which shares a lot of the same features as the toric code, there's a threshold at the code capacity at 1/2. And for 2 dimensions, you get this number of about 7.5%. So experts will note that that's a good but not amazing number. Okay. Cool. Now let me, yeah. A little, like basically 11%. If you restrict yourself to local decoders, this is better than other stuff by factors of 3 or 4. But if you do maximal likelihood decoding, then you get 3-ish% more. Yeah. But I haven't spent any effort into trying to make this number bigger, so we can, yeah. Cool. Okay, let me then in the last little bit talk about the more important question of online decoding. Okay, so now instead of just getting a noisy state, we're going to have to actually stabilize state in an unreliable environment for a long time. Okay, I left this to the end because hopefully, if you followed the offline decoding part, this one will be pretty easy to understand. Okay, so online decoding. So when we're doing quantum error correction, this is kind of paraphrasing a quote by Gottesman that I like, is we have to face our own failability. Okay, so we, as the error corrector, introduce errors into the system no matter what. Okay, so our measurements are imperfect, noise is always occurring. Okay, and what we want to do is we want to find a online decoder now, which basically retains the state in a way that can be decoded for a long time. So we're trying to find an online decoder such that when I do noise and the decoding dynamics for a long time, I get a state that can be decoded to the correct logical state with high probability for a long time. Okay, so this is what we're trying to do. And the physical significance of this is if you have such a local online decoder, you have what you might think of as a stable, absolutely stable phase of quantum matter. So see Tibor's paper, for example, for inspiration on that.
Like for T, or the proper definition T, like scales like.
We want T to be long, right? Well, we want it to be as long as poly L might not be good enough. We might want it to be exponential in L, but we definitely want to have it diverge with system size. Yeah. So let's just ask, how does our decoder do when we're in this setting? So measurements are unreliable and noise is happening all the time. Well, here's how it does. Let's just watch a movie, right? So, I mean, this is obviously not going to tell us anything, but what's happening here is errors are constantly, messages are being produced and transmitted constantly, anyons are moving around, and you get this like bubbling soup of anion pairs that are popped into existence and then killed right away, right? Okay, this is a movie. This is not telling us anything quantitative. If we do Monte Carlo simulations, though, oops, that's not the art. Okay, sorry, getting ahead of myself. Let's be a bit more quantitative and actually diagnose how well it's doing. We're going to do that by defining the logical failure rate in this way. So it's just the probability that we can correctly recover the logical state after time t. Okay, so this is the logical failure rate, and yeah, sorry, this time t here in this expression should be taken to be the system size. Sorry, that was a typo. So we evolve it for a time equal to the system size, and then we try to decode, and our success probability defines the logical failure rate. Okay. Okay. Yeah.
The time is L, the spatial scaling is the same.
Yeah, L. Yeah.
The space and time and scale on L.
Yeah, that's a nice way of so we're trying to define a logical failure rate, and it's nice to evolve for a time which is the same as your system size, so you get like a even aspect ratio space-time box under which the error correcting dynamics is happening. You can make other choices if you want, but yeah.
So you would get a measure the observe the correlation between some
Yeah, in an indirect way you do. So you evolve for a time L, then you stop the evolution and you ask, can I recover my initial logical state by doing some decoding procedure? Okay. So does that make sense? Yeah, okay. Okay, so again, we're to just get a rough estimate, we're first going to do numerics in Monte Carlo. And I just showed the numerics here for the 1D repetition code, but the toric code is similar. And you get something which looks nice. So why does this look nice? Well, I'm plotting the logical failure rate against the physical failure rate for different system sizes. And what you're seeing is that as I increase the system size, the logical error rate is going down. And it's going down in a way which is indicative, perhaps, of there being a phase transition, of there being a threshold. So it looks encouraging. However, there's some bad news, which is that these models don't actually have a threshold. So you can show that as you take the system size to be larger and larger and larger, the logical failure rate actually just goes to a constant. If this model had a threshold, the logical failure rate would go to 0. Okay, but here it's only constant.
Just even for that 1D repetition,
Yeah,
they're moving slowly, so that's
there's a finite drift. If you look at this, so you're supposed to get a crossing of these curves, right? So if you look at the crossing is slowly moving towards smaller p. And you might think that this is a finite size effect. The authors of the field-based decoding paper, Izard et al., they also thought it was a finite size effect, but it's not a finite size effect. I mean, in some sense, it doesn't matter, but let me explain why this is true. So yeah, this is the result. They don't have thresholds. And here's a very fast quote proof of this fact. Okay, so consider the distribution of anyons that are present in my system at any given time. You can ask about the expected size of the largest anion pair. Okay, there's a very simple estimate that tells you that this is about log of the system size. Okay, so maybe it's like 30 seconds. I'm not going to go to the exact estimate, but the point is that it scales as the log of the system size. So with very high probability, there exists a pair whose separation is log of system size.
what is the intuition on
What's the intuition?
threshold?
The threshold. There's no threshold. I'm trying to explain the fact that there's no threshold. So here it looks like there's a threshold that's like 5%. So sorry, there's a discussion happening. That's
Ignore that.
no talking during class, you guys. But if you have a question, raise your hand. Is there a question? Sorry. Okay. Sorry, that was too channeling Mrs. Lawson, third grade. Anyway, yeah. So let's go back to this proof. So we have this one large anion pair which is separated by a distance log L. Remember, these are sending messages to each other, right? Basically, the intuition for the proof is that log L goes to infinity as I take the system size to infinity. That means these two anions in this pair are separated by an infinitely large distance. That means they'll have a bunch of small anion pairs in between them, which are caused by the noise, right? What's the distance between these anion pairs? That's about 1 over square root of p. P is the error rate. So the average distance between these pairs is like 1 over square root of p. So this distance is much larger than the distance between anion pairs. Remember, we're moving in the direction of the nearest anion. So the anion nearest to this one is never going to be correlated with the position of this anion. The nearest anion is just going to be some random pair around it. Okay. This means that the anions are just going to diffuse. This pair of anions that are separated by a large distance, they just diffuse in a random direction. Okay. Having them be corrected would require like an uninterrupted communication channel in between these two anions. And that communication is always going to be blocked by these small pairs in the middle. Okay. So you just get diffusion at large distances, and diffusion is just the same thing as you'd get if you didn't do error correction at all. Yeah. Any dimension, yeah. Yeah, this argument is very general. The only thing that depends on dimension is the power of 1 over p here. Yeah. Okay. So this means there's no threshold. However, this argument, this problem only sets in when we had this inequality, when the distance between the anyons in the large pair was much bigger than the typical separation, right? So that only happens when, that's only a problem when your system size is bigger than e to the 1 over square root of p, right? So when p is getting small, this size is getting very, very large. And this behavior, which I'm going to call a pseudo threshold, makes it very, very hard to distinguish in numerics between something that has a threshold and something which doesn't, right? If we as theorists are interested in there's an actual phase transition here, there's an actual threshold, then this type of behavior is extremely difficult to distinguish from true threshold behavior. If you're an experimentalist, you might not care. Having something that looks like a threshold up to system size, 10 to the 17 is still good enough. But nevertheless, there's no true threshold. Okay. Then now let me very briefly describe a way of fixing this. Okay, so I would like to produce a decoder which does have an actual threshold. I'm not really satisfied with the pseudo threshold. So I'd like to get an actual phase transition. How is that done? Let me just briefly describe how that could be done. The easiest way of doing it, there are more complicated ways, I'm sure, but the easiest way is to add a small extra dimension to your system and use it to do a little bit of RG, a little bit of error correction. So people who know about window decoding, this is kind of how this is working, but I'm just going to explain this kind of heuristically. So we're going to add an extra dimension to our system. So we're going to have our 2D quantum system, but now we're going to allow the classical processors to live in like a 3-dimensional lattice. Okay, so this extra dimension is going to be pretty short. It's not going to have it's not going to be very deep, but nevertheless, we're going to add this extra dimension. Yeah, what's up? You can choose how short it is, and your threshold your error suppression will change accordingly in a way you'll see.
If you have a log L, that's for the surface code it is syndrome measurement.
Yeah,
that's already pretty good.
Well, thank you. Yeah, you'll see what the extra, I haven't explained to you what the dimension does yet, right? So so here's how it works. So you have anyons that are created in your system by noise. And what you do is you just move these anyons up the extra dimension until they like accumulate on the top surface of your extra dimension. So they're just getting moved up during the dynamics. Okay. And while they're getting moved up there, you're running this offline decoder message passing thing that I just described on them. Okay, so what's going on is when you add this history of anyons and you're pushing it into the extra dimension, you do offline decoding on this accumulated history. What happens to anyons is that they become exponentially more dilute as they move up in this direction, right? Because as they start moving up, they start doing error correction, and all the close by anyons have annihilate themselves. So what you should think of is that by the time the anyons get to this top surface, all of the small pairs have already been annihilated, and then this problem that we just discussed doesn't happen. Okay, so
feels like it's philosophically similar to having a syndrome extraction rounds log L, then it already performs pretty well.
Syndrome extract. Well, I can't do log L syndrome extraction rounds in between the noise, right? Each application of the noise. So oh, sorry, that's what you meant. So the processing time and like the time scale on which feedback operates has to be order 1.
Yeah.
Right? And so here we're requiring it to be order 1. If I can do log L, if I can do a log L number of steps in between each noise event, then yeah, it's very easy. It's much easier to get a threshold. When I can only do 1 feedback event in between noise events, it's much harder. So here, there's still a log L showing up, but it's not in a speed or a divergence of a communication or anything. It's just in a extra spatial resources. not in time
And
resources,
It's a spatial quantum resource or?
classical resource.
Classical resource.
Yeah. So yeah, that's another way of saying I'm not comfortable with having quantum operations, be they measurements or feedback or anything that diverge with the system size in any way, but a classical memory, I'm okay with. Yeah. So spatial classical resources are going to be cheap, but not free for me. And then temporal resources are always going to be expensive. Yeah, let me just show a movie how this works, because this is going to illustrate. So I'm going to be in one dimension, the repetition code, and here's what's happening. So these anyons are being created down here. They're like boiling up to the top, and they're getting error corrected as they go. And the fraction of anyons that actually make it to the top and is reduced in the depth of this extra dimension. Yeah, hopefully that's intuitive now with the movie.
Extra dimension is a classical syndrome.
It's completely classical information.
Syndrome
Yeah.
history, and then when you're now trying to
Yeah.
pair things up, you actually doing the quantum register.
Well, it's all classical at the end of the day. So you're pairing things up, and you're saying, okay, what operation did I need to do to pair these anyons? Let me write that to some classical memory, and yeah, everything is kept in the poly frame if you like. Yeah. Yeah, and so there's a you can prove a theorem which is that as long as this depth of your extra dimension increases with L, you have a phase transition. The bigger the depth is, the better your logical error rate is suppressed. But if you just want a phase transition, then you could take log L if you like. Yeah, okay. Some numerics. Again, the numerics are going to be a little bit misleading right now. Now these are numerics with a threshold. The earlier ones had the pseudo threshold thing. But the threshold value occurs at about 1.5% for the toric code, which is good. It's better than Harrington by a lot. Not as good as it could be, but yeah. Okay.
You see like that number staying when you change the number of bits that you're storing for
Yes, it's yeah. So the value of the phase transition doesn't depend on the number of bits. The only thing that depends is how rapidly the logical errors are suppressed. Yes.
Is it clear that what you see in the numerics is the actual threshold and not some sort of threshold?
No. I mean, a pseudo threshold doesn't happen in the system when I take the depth to get larger with system size. Yeah.
I guess we get something like there's like something that looks like a pseudo threshold and there's like a small actual threshold.
So it would be to me, it would be very strange if like the threshold was like 1.5% for system sizes that I can simulate, and then it went to this true threshold, which was like suddenly at smaller system sizes. That would be kind of perverse. No one is going to be able to prove that can't happen, because no one can calculate the exact threshold from first principles. So you could ask that question about any error correcting code. Yeah, sorry, I'm going a bit over time. Let me just wrap up quickly. So one thing that I think is kind of interesting from a condensed matter point of view is you can look at the transition that occurs as memory is lost in 1D, and it appears to be a continuous phase transition with these critical exponents. I don't know if these look familiar to anyone, but as you know, why this is interesting is that phase transitions don't occur in one-dimensional equilibrium systems. This is a phase transition in a one-dimensional system which has a local order parameter that it undergoes a continuous phase transition. So how do we understand this from a field theory point of view, et cetera? This is something that I haven't thought about. If people have ideas, I'd love to hear them. That was the kind of last thing. I think I just want to end on a little bit of outlook. So this was the summary of what we accomplished today. There are some immediate questions that you would have. So there are some like obvious extensions to non-abelian phases, et cetera. One thing that I'm particularly interested in is understanding if we can stabilize non-equilibrium memories in one dimension. So I mentioned that there's been some work in the classical setting on this by this guy Gatch. and I also mentioned that it's impossible to understand. I just wanted to illustrate that. So this algorithm 19.7 is from page 189 of his paper. This is one of order 100 algorithms that go into the construction of his automaton. It involves like things that are doomed, right? And like germs that grow, and it's impossible to understand. I've spent a lot of time trying to understand this paper, and I feel when I'm reading it that it's like the blueprint of some crazy genetic organism that like time traveled from the future. It's crazy. So I would really like to understand if there are simple ways of stabilizing non-equilibrium memories in one dimension. Yeah, I have some thoughts. People can talk to me afterward if they're interested. For any practical people in the audience, the decoders we constructed today are the fastest decoders I know of, and they're pretty accurate. So they're much better than other existing cellular automaton decoders. But to really compete with the state of art, we need to maybe tailor the exact rules that we used for superconducting hardware. And I think it would be useful to do maybe some ML guided searches for nice update rules that improve your threshold. And then, okay, just because, I mean, I've been talking to some people will recognize this image from things that I've been showing around at this conference. But, what I talked about today is the problem of preserving information in an adversarial environment, right? And this is what biological organisms do during homeostasis. And so we might ask, well, beyond just doing homeostasis, what kind of emergent phenomenon can we have in cellular automata or other types of simple systems? So like, what is the simplest setting in which you could have emergent lifelike phenomena? Okay, this is going a bit. Anyway, if anyone's interested in this, let's chat afterward. Okay, thanks for sitting through it. Yeah, thanks.
Okay, I will take maybe 2 questions.
Yeah. Thank you for a nice talk. I just have a simple question regarding your decoder compared to some kind of local version of Union Find decoder. So yeah, it seems like the cluster generating things is quite similar to Union Find, right?
Yeah, so you could think of this as a attempt to make Union Find completely local. So
Okay.
either Union Find or minimal weight matching or any of these things, if you try to do them in a local, completely parallelized way, this is sort of the only thing that you can do. So you can measure syndromes, you can pass messages about where the syndromes are, you can do something based on that. And if you require that things be translation invariant, you're going to end up with a scheme like this. So the starting point can be thought of as trying to parallelize Union Find, if you like. Yeah.
Okay, I see. Thank you.
I wonder if it makes sense to increase the travel speed later in the process. Then maybe you need more locality by some log n, but you could decrease the time.
Yeah, totally. Yeah, indeed. So especially in this decoder where you're having the bubbling, right? This thing. Oops, sorry. Yeah, you could definitely, if you have some notion of like total amount of non-local communication as some fixed resource, yeah, you could distribute that kind of preferentially towards the top layer of the simulation. What's going on here is that this extra dimension is like explicitly separating out errors at different scales. So this is like an RG direction, and then yeah, you could indeed distribute more of those resources towards the large scale part of the RG. Then that might help a lot. But understanding like what exactly the cost function you're trying to minimize in terms of the amount of non-locality you have available to you sounds like maybe kind of a detailed question. I'd have to understand more about superconducting hardware to know what the best way of approaching that is, but sounds like a good idea.
Okay, let's thanks the speaker again.
Yeah.